Thanks for coming. My talk is called Turning iOS End-to-End Testing Up to 11. Hopefully what that means will become clear over the course of this talk. Just to get a feel for the audience, how many of the people here are invested in iOS end-to-end tests or UI tests? Excellent, that's a sizable number. So a little about my team. I work on the end-to-end automation team at Facebook London. We're based just off Euston Road, so not far from here. We manage the infrastructure and frameworks that are used for building end-to-end tests for Facebook engineers worldwide. We cover iOS, Android, and tests for web browsers. End-to-end tests in our world mean taking an application and running it against production services with test users that we use. We cover a wide range of features in our core applications. Obviously, Facebook, Messenger, Instagram, and others. A typical interaction that you might expect to see in a test is we have a test user, the test user logs on, makes a post, and another user can like that post. That's a simple example. Cool, so maybe some of you were at Selenium Conf last year in Portland. One of my colleagues, Remy, gave a talk about how we scale end-to-end tests more broadly, particularly in relation to the way that developers work, and also touches on some of the abstractions that we used. You can check out the video here. Fortunately, these things are recorded, which is great. So please feel free to check that out. Right, so let's get started. Here's the agenda for today. We're going to cover very briefly the good and bad of end-to-end tests, and then the tests, the challenges as they apply to UI tests on iOS. Following on from that, we'll look at stability and performance, and how we can substantially improve that. Following on from that, we'll look at WebDriver and iOS together. Then we'll take a look at one of the solutions that we have there, FB Simulator Control. And I'll finish by recapping. Cool, so what is good about end-to-end tests? I think the thing that always comes up is coverage. You can cover a huge part of your infrastructure, your applications. You can tickle parts of your application that you never covered it with unit tests or integration tests. You can test your back end at the same time. So there's obviously a huge part of your systems that you can cover. But what's bad? Obviously, coverage being an issue, coverage being so big, isolation becomes a problem. This means that it can be very difficult to figure out what went wrong with your tests. The understanding of your tests can also be an issue. So when things go wrong, how do you know what went wrong? Sometimes you need to keep breadcrumbs in order that you can reproduce things. And it becomes very difficult to understand what went wrong. Performance is also a big issue with end-to-end testing. You have to boot up a browser or simulator or get running on a device. You're also running against an asynchronous user interface. You're not testing an individual unit of code in a class. Stability is also hugely problematic. We hear about flakiness at this conference. Stability also in your infrastructure. Sometimes booting a simulator for end-to-end tests can be troublesome. We'll cover these three topics today. Isolation, I won't be covering much in this talk. So let's look at iOS UI tests and the challenges thereof. So on iOS, you test your application via the Xcode framework. This means you write your tests in Objective-C or Swift. The Xcode framework itself is an Objective-C framework, so you can write your tests in Objective-C or Swift. It was added a few releases ago, so in Xcode 8, iOS 9, it was added just over a year ago. And since tests test the entire application, the application must be running. So this means you need a booted simulator with the application installed. Yes, the way that it runs is that a test bundle runs inside a test host application for controlling the app under test. I'll expand on this a little later so you can see how these things interact. And how you run these things is either in the Xcode application that you all commonly develop in, and this can be automated with the Xcode Build command line. So let's look at the life cycle of a UI test run on a simulator so we see what's going on. So I'm going to start with an x-axis, which is time. These timings are pretty rough, so they're for illustrative purposes only. I'm going to assume we're going to run UI tests against a booted simulator, as I previously mentioned. And a key part of this is repeatability. So commonly, you'll erase the simulator before running tests against this. If you have a logged-in user, you're going to want to make sure the next time you run a test, the user is logged out, so you have a fresh application. You then boot the simulator. This does take some time. It appears to be somewhat I/O bound, which is interesting. Then you install the application on that simulator in order that you can run tests against it. Then you can finally run the UI test. As you can see, the prior steps are in red. The meat of what we want to do is in green here, which is run the tests. Everything else is in service of that, of running the test. Then we shut down the simulator. This is in order that we can start the process again. So waiting on simulators slows down test runs. Like, we only want to actually run the tests. The other steps are just necessary in order to fulfill a number of needs. So what happens if we have multiple tests that we want to run? Well, we start off with the time series again. We erase, we boot, we install, we run the first UI test, test A, and then we shut down. So if we want to run a second, well, we do this all over again. We erase, boot, install, and then shut down. If we want to run again, we erase, we boot, we install, we run UI test C, and then we shut down. So this means that test runtimes will scale linearly with the number of tests. And linear scaling can be okay a lot of the time, but when you want to scale the number of tests that you run and the number of times that you run them and when you run them, this soon becomes an issue. And we really don't want to disincentivize writing more tests. We want to be able to cover many features of our application and so on. So we don't want to make developers unhappy by scaling linearly with the number of tests that we run. We love tests. We want to be able to scale on our own terms. It would be great if we could scale non-linearly. So what is one way of this not being the case? So the iOS simulator doesn't use a whole lot of resources when you're actually running a test. Obviously, iOS is a mobile platform. It's heavily optimized for mobile devices and battery usage and so on. So we could indeed run the tests in parallel like this. That would be great. We'd get increased test throughput. Obviously, the aggregate time or the time to run a single test would be slightly slower because you're obviously loading the system. But since a lot of the tests are just waiting on networking and asynchronous UI and so on, turns out there are a lot more system resources free than you think. However, we'll find that this isn't necessarily the case out of the box. So let's look at the components of a UI test run on the simulator and how they fit together. So I'm going to start off with Xcode Build to start the test run on my Mac. This will then build the app under test. We obviously need to build the app to run tests against it, and also build the test bundle. This is where the meat of your UI testing code is. Of course, once this is done, the simulator then appears, and we have iOS. We can start running tests. So Xcode Build requests that the test host application is launched on its behalf, and it does this by talking to iOS through a socket, basically. When that's done, the test bundle can run inside the test host app. This has changed in the latest Xcode, but broadly speaking, you can just think of this bundle running inside this host application. And when that's done, the test bundle can request that the app under test is launched on behalf of the test bundle by talking to iOS. So let's take a closer look at Xcode Build and what this actually does. So Xcode Build is the executable for iOS build and test automation. It does, however, lack streaming output for tests. This means that it can be somewhat difficult to integrate into continuous integration systems, so you see a number of third-party solutions for doing this. Some modify the test runner, others try and parse the output to get it to something more structured. Obviously, you can get some structured output with this dash result bundle path argument. This will output a test result bundle, as they call it, which contains a lot of screenshots every time a UI interaction happens, as well as more structured output from the test run, but this happens at the end of the test run. And you can get some diagnostic data from this bundle. There are screenshots. There isn't any video, unfortunately. Interestingly, screenshots, depending on the number of steps within your UI test run, the size of all the screenshots together can actually be larger than a well-encoded video, which is kind of interesting. And since Xcode 8, we can use this new test without building argument. This means that you can build your app under test and test bundle once, and then run it many times on different hosts if you wish. However, there is an internal limitation with simulators. I'm talking about simulators here, not devices, which is that you have these multi-core Macs and you have a single iOS simulator running on them. Obviously, we're wasting a lot of the resources that we have there, so it would be really cool if that wasn't the case. And you use XCTest or bust, basically. This, for a lot of iOS developers, is perfect. It's very natural for people. However, when you have cross-platform teams and so on, I'm sure many of you have experienced this. If you have tests on not just iOS, but Android and other platforms, that maybe having the same kind, writing the tests in the same way can be beneficial. So let's look actually in more detail at what the critical path of running a test run could actually be, rather than what we get off the shelf. So by this, I mean we're going to look at the dependencies and how they fit together. So we've seen this before. This is the test run in parallel. Not possible at the moment, but I'll take it a step further and we can figure out how to make it better. You can do this kind of optimization with test without building. If these were separate hosts, because one host can run one simulator, therefore you would run these all on separate hosts. However, we can consider the first part of this, prepare simulator, as we call it. This is mainly so it will make more sense of the graphics coming up. So what we do actually have is we have this big thing, which is the build, which is the dependent step for running tests. Now, the building of the application is actually independent of preparing the simulator. You can launch a simulator without needing a build. Yet, obviously, to run the tests, you do need the build. So we could reconsider this approach and build and then prepare our simulators in parallel. This means that as soon as the build is finished or the simulator has booted, whichever is the slowest, we're now ready to run the tests. Obviously, we have to install first, so that's what we're going to do, and then we can run all of these tests. So as you can see, this also changes the dynamic and has the potential to increase test throughput. Hopefully, we can use this knowledge later. So what do we call this? Well, we call this hot simulators. This means that the simulators are ready to run tests as soon as the build is ready. By splitting up the relationship and figuring out our critical path. This means, obviously, the simulators are ready to accept tests. So instead of having tests waiting on simulators, you instead have simulators waiting on tests. So I'm going to introduce something new now. We have the test host. What if we ran the simulators on a separate host? So we still have to build the app under test. Obviously, we need that for the tester function. I'm going to hide app install in these slides, by the way. So what we can then do is prepare a number of these simulators in parallel on a separate host. And then when it comes to run the test, they can be run on simulators 1, 2, and 3. Now, this is assuming we have 3 test threads on the test host. Now, when we're ready to run tests 4, 5, and 6, we would have to reboot the simulator, etc., for the first 3 hosts. But we have 3 other simulators that are now ready. This is really good. We don't miss a beat on the successive tests that we want to run. This reduces test run times. Now, once the simulators are done running tests, they can start to prepare themselves again to get ready for the next test that wants to run. So they're, again, hot for the next test. So how does this apply to stability? Well, there are actually some really interesting properties of this approach that means that stability can be enhanced. So let's take a look at the same diagram again. This time we're going to run test 1 and test 2, slightly different run times for the tests, perhaps. Now, what happens if the third simulator has an issue booting and it's gone? Well, that's not great. We still need somewhere to run the test, and we want to run test 3. So we still have another simulator hot and ready to go. We can just use that one without missing a beat. It also means that the simulator that previously failed to boot can be restarted. And the process begins anew, moving on to the next set of tests. We're not affecting test run times by a few simulators having issues. And we can absolutely do this on multi-core Macs. There's no reason we shouldn't be able to do this. And obviously, the preparation of the simulators begins anew for the simulators that have finished running tests. So let's have a look at the overview of stability here. Test stability is not necessarily affected by simulator stability. That's a really nice property to have, especially if simulator instability is a common cause of test flakiness. We can remove that entirely. We never give out bad simulators to tests. Maybe a simulator says it's booted, but there are some other issues. We can also check those before handing them out to tests. And it also means that the app install can occur before running the test, so you can start to prepare simulators for the next test as you've already built the app. So you can start to look ahead towards the next tests that are running. It also means that you can get a high test concurrency. Tests themselves, if you're using WebDriver, don't tend to use a whole lot of CPU. You're just sending some JSON over the wire. You can, on many machines, have very high concurrency here. There's also moderate simulator concurrency. Obviously, the simulators are running a simulated iOS, so there's going to be an upper limit on the number that you can run on your Macs. Which means that one test host can address many simulator hosts. So you can even have a situation where you run more tests, so you have more machines running simulators than you have machines running tests. But how is this possible? Obviously, I said Xcode Build has an internal limitation that means that you can only run one simulator on one Mac at a time. To do that, we're going to look at WebDriver and iOS. I imagine a lot of people here know what WebDriver is and have some experience with it. So I assume I'm preaching to the choir here. So let's take a closer look. macOS Sierra now has Safari driver, which allows macOS to use the WebDriver protocol to manipulate Safari. You can also fake an iOS Safari with user agent, it also has a way of setting the screen size for to test mobile websites. However, there is no Safari driver for iOS mobile Safari. Mobile Safari is the name of Safari on iOS. So we can't test Safari on iOS using mobile Safari. We can on desktop Safari. And UI automation is gone. We heard about this earlier in the conference. It disappeared this year. This was the old way that you could automate the whole OS. So now the new framework is XCTest. So we're going to have to use that. So we're in a situation where you have to bring your own WebDriver for iOS. So it turns out we did bring our own WebDriver for iOS, which is WebDriver Agent. We open sourced this for the first time last year at Selenium Conf in Portland. And it is a WebDriver, it was at the time, a WebDriver server implementation for iOS using the UI automation framework. You can see the GitHub page there. However, over the course of this year, we migrated to the new XCTest framework, knowing that UI automation is deprecated. And we're now running on the XCTest framework, which does change the execution model to using test bundles, as we saw earlier. So let's take a closer look at WebDriver Agent. It's built on top of those XCTest UI testing APIs, so it uses the same automation primitives that you'd use for testing your application directly, except it's implemented in terms of the WebDriver protocol. It runs like a regular XCTest bundle. We'll see a bit later how that works. And we're working towards implementing the WebDriver spec. We're a lot better than we were a year ago. I think we're in a very good position now. So obviously, if you have any issues, feel free to raise bugs with us. But we have come a long way over the last year. And it's an endpoint node in WebDriver parlance. So that means that a single instance of WebDriver Agent does not manage multiple simulators. It's not like it's not part of a grid or anything. Of course, you could integrate it into a grid-like system by having a proxy or some other thing. And it will start the app under test on session start. So this means that it fits within the sort of common semantics of the WebDriver protocol. So when you start a session, it will start the app under test. And we've added a few things to make hot simulators more possible and more easy to work with, like the health check endpoint. So you can, I think, send a get to this health check endpoint, and it will tell you whether the driver is in good state. There is some flakiness within the UI testing frameworks that we try and protect against, so that's why this health check endpoint exists. And it has an inspector built right into the web server. So if you've booted WebDriver Agent, you can pretty easily hit the inspector endpoint, which is this. So it's like the host name, the port that you've bound on, and /inspector. So you can open this in a web browser. So here is Safari in a web browser using WebDriver Agent. We have a screenshot. If you refresh the page, you'll get a new screenshot. We also have a tree of elements. So you can drill down, and I believe if you click one of these, it will also highlight the element in the inspector. On the screenshot, it will overlay this. There'll also be some details about each of the elements as you select through them. So this can be very helpful for debugging. You can pause your tests, open the inspector, and see what's going on in your app if things aren't as you expect. What's also really cool is that we have a tree endpoint which will serialize this to a JSON format, so you can fetch it at any point and save this for later. This becomes quite handy when debugging. So let's take a look at how we run WebDriver Agent. We have a Mac running Xcode Build, and we have a simulator running iOS, running on that Mac. As before, we have a test bundle, except this time the test bundle is WebDriver Agent. So we can start the test bundle host again, and except this time, we're going to run the WebDriver Agent XCTest bundle within the test bundle host. Now, WebDriver Agent is technically a test itself, but once it starts the test, it's like, hey, now I'm a web server. So it will just sit there waiting for a session start, essentially. And then, when you're new test runner comes along, which is now external from the Xe test bundle, it can use the JSON wire protocol to start a session. And starting a session will launch the app under test in a similar way to UI tests did before. So now we can see that our test runner is external from the test bundle. So you can use the JSON wire protocol to do as you wish in your tests. So what are the benefits of having this external test runner, which means driving test runs outside of an Xe test bundle? A test runner is a WebDriver client, as we expect. We're going to use the WebDriver protocol to manipulate the UI, which is what we do here. We're going to manipulate the UI of the app under test using the WebDriver protocol. It also has affordances for hot simulators. You can boot WebDriver Agent after you've booted the simulator, but before you run tests. So again, you can see that this is useful for the hot simulator approach that I showed in the sequence diagram earlier. And you can build your own languages and abstractions. There's a vibrant community out there of different ways of writing tests, different languages, different idioms that you want to use. That means that you can now do that, like you just implement this in terms of the WebDriver protocol. The test runner itself is also now running outside of the iOS sandbox. So if your test runner wants to do something else other than interact with the app, you can absolutely do that. Which means you can assert on external services. So your test runner can start to hit other parts of your infrastructure, and you can perform assertions like, did this thing actually happen? And it isn't shown in the UI. You can also, because you're running outside of the test bundle, not inside the sandbox, you can collect diagnostic information from iOS itself. Well, how do we do that? So this is where FB simulator control fits into the picture, which gives us both parallelism and diagnostics. I'll focus on parallelism first. So what is FB simulator control? It is a macOS 10 library for managing, booting, and interacting with multiple iOS simulators simultaneously. It's a bit of a mouthful. You can look at the README there. So let's take a closer look. It's an Objective-C macOS framework. We were pretty clear about it being an Objective-C framework because this means that we don't enforce a Swift version dependency on users. That might, depending on your usage, that may or may not be a problem. And it follows many of the idioms of Objective-C. It supports multiple simulators, both headlessly and with a simulator app. What do I mean by headlessly? So headlessly means that the simulator application itself isn't launched, but the underlying simulator is still there. In automation workflows, you probably don't care that there is a simulator app about, like you just want somewhere to run your tests. You can, of course, still use the simulator app if you choose to do so. There's no limitation there either. And it has built-in resilience to common causes of failure, so this gives us some additional stability with the hot simulators. So there are a lot of strange races when managing simulators, like if you and common pitfalls. So let's say you try and erase a booted simulator, you'll get an error. Like FB simulator control will try and do the right thing. So in order to erase the simulator, it has to shut it down first. It does a few things like that. It can also launch apps and test bundles on multiple simulators. So the big part here is the launching of test bundles, which means that if you can break the issue of only running one simulator on one Mac host, you can now run multiple and run WebDriver Agent in those simulators. There's a few hacks, I guess, in order to afford this, but like it does mean this works really well and it's quite stable. It also supports video recording of the entire simulator. So we have a way of accessing the frame buffer of the simulator, which is where all of the applications and the whole of the OS is rendered. And we can pull this frame buffer out and then encode this to a video. Now, by the looks of the changes to the internal frameworks in Xcode, it looks like this may happen at some point in the future out of the box in Xcode. But for the time being, FB simulator control can do this. It also has quite a rich diagnostic API and some common diagnostics. So you can fetch system logs, crash logs. You can even fetch screenshots. And these are, again, screenshots taken straight from the frame buffer. There's no modification of the applications that you launch that you have to do. And it will also work with Springboard and Safari and so on. And it works across Xcode versions. This helps in the deployment case. So you can build once and run on different hosts, which may or may not have different versions of Xcode on them. And there are a number of ways that we make this happen. But the important fact is that many of the features do work across Xcode versions, and therefore iOS versions. However, a framework in itself isn't particularly easy to integrate with in CI systems. So that's why we came up with FSMCTL, which is a command line interface to the FB Simulator Control framework, and it intends to expose the core features of the FB Simulator Control framework. It's inside the FB Simulator Control repo. It uses FB Simulator Control to get its stuff done. Now, let's go into a bit of detail about FSMCTL. It is FB Simulator Control with batteries included. What does that mean? It means do what I meant. So we have smaller primitives in FSMCTL. There is the SimCTL command line as part of Xcode. We have many similar features there. We do have test bundle launching as well. But do what I meant also means that you can omit many arguments. For example, if you have a simulator booted, you don't, when you want to install an application, you can just do you'll see the command, but you can just run an install command, and it will assume that you meant to run this command against the booted simulator, because you cannot install on a simulator that is not booted yet. And you can combine these to make some pretty powerful systems, including the ones that I've described earlier. And you can easily install it via Homebrew. This is the de facto standard for command line applications on macOS, so you can just install it via Homebrew. And it's mostly Swift. We chose this because it makes it very malleable and hackable, so it becomes very easy to add features and so on. We want the FE Simulator Control framework to be very stable, but having a playground to experiment on new features is a really great thing to have, and like Swift is quite good at affording that. It also provides structured output, which aids in the integration with your continuous integration systems. Many of the existing command line tools that exist within the Xcode ecosystem that comes out of the box with Xcode don't necessarily have structured output, which means you end up having to pass strings and so on. If FSMCTL can output each event to a single line of JSON, which means that the caller of the process can do useful things with that information. And it also has an integrated web server. This means that you can control a simulator remotely from another machine. So how do we do stuff with this? What I'm going to do is have a few commands just to demonstrate this. This is going to get simulator ready for running tests using WebDriver. So we're going to boot the simulator. Here we run FSMCTL. This thing's called a UDID. Each simulator has its own UDID. So we say boot the simulator. And then we can install an app on it. So we go FSMCTL install, and then the path to an application. I've omitted the UDID because FSMCTL can reasonably assume that you mean to install on a booted simulator. Now, this is a bit more complex, but what we're going to do is launch WebDriver Agent, and we're going to inject it, WebDriver Agent is going to run inside the test bundle host of the preferences application, because it's all installed on all iOS simulators. That will be the test host, and then we're going to start WebDriver Agent on port 8090, and this will keep the connection to WebDriver Agent alive until you send a signal to FSMCTL. You can send a sig hub. So this is what it is: FSMCTL launch XCTest, the test bundle, the bundle name, which is com.affle.preferences, then -- port 8090 is the port, it is an argument that's sent to WebDriver Agent. And then listen is just there to keep the process alive. We need to keep the connection alive because this is the way that like Xcode Build works. So we can also, in addition to this, alongside the WebDriver server, we can start another web server, which is the FSMCTL web server. So we can do FSMCTL listen -- HTTP 8091. This means that obviously the ports don't collide. So how does this work? Well, we replace Xcode Build with FSMCTL. We still have the external test runner. And now the test runner can communicate to FSMCTL additionally over HTTP. So they can just hit two different endpoints, whether they want to control the simulator or whether they want to control the application under test with WebDriver Agent. Now, we can consider this to be one unit of work, actually. And we can also have many of those units on one host. So here we go. We have one FSMCTL running on a host and a test runner connecting to it over HTTP. We have a second one and a third one and so on. Now, since we're using HTTP as our medium, that means that these two machines can be different. We now have a simulator host and a test host. That's great. So just to pivot back to the diagnostics, which is an API for querying and fetching them, and we have an API for querying and fetching them. It gives you logs. You can access logs for the entire simulator. This can be very helpful when debugging what's gone wrong in your tests. There's also a search API, so you can send off a batch search request if you want to scrape specific parts of the logs of a simulator. You can also access screenshots using this API. You can also yank out the contents of the documents directory of an application that you've launched. So maybe your application has a bunch of additional logging data that you put alongside that you might want to present later in the case of a test failure. You can yank all that out at any time during a test run. It also allows you to control the video recording of the entire test run. And these things are all queryable. So additionally, there's like even an API for querying the crash logs, and you can use timestamps and kinds of, there are different kinds of crashes that you can filter on as well. So let's have a quick look at how you'd use this. So this will start the video recording, FSMCTL record, start. This means that you can keep the video the listen means that you can keep the video recorder alive until you send it SIGHUP. This gets the path to the video diagnostics, so you can use that video as you see fit, so you can upload it somewhere if you wish. This finds Spring in the name Spring in the system log. You can also do the same with over HTTP. So I'm just going to have a host, which is the host name, the FSMCTL port, and also in the path you can put the simulator UDID, so you only target an individual simulator. I'll breeze through this. This is like a post request that starts the video recording. We can also get the video diagnostic, and it will base64 encode the content of the video, which means that we can restore it locally into an MP4 on the machine that's requesting this. We can also do the same with finding Spring in the system log of all booted simulators. This uses a search query to find these things. So this means it's easy to call from your test runner. So finally, I'll look at the how we use this at Facebook. So this is what we call the diagnostics page. This is what we show for all test runs, all E2E test runs. To take a closer look, here you can see the name of the test, some information about the test. Down here, we have the screenshot. This is collected at the end of the test run. You can even see the duration of the test, which is actually lower than than we've had previously, because the simulator's hot. We don't incur the cost of booting the simulator inside the test run. Additionally, we have some additional diagnostic tabs. Here you can see the reason the test failed is because the app crashed. Here we also collect the video and upload this, so any developer can go back and look at the video of the test run later. We also have what we call the element tree, which we scrape from WebDriver Agent. This is taken at the end of the test run. As you can see, it contains all the elements that you see in the screenshot, so you can see the home screen there. And finally, one of the other tabs we have is the simulator log, so you can go back at your leisure at the test failure and figure out what went wrong in your test run. So, a quick summary. iOS tooling has many convenient defaults in Xcode Build, but flexibility is also desirable. The critical path of your tests isn't necessarily as it first appears, so extracting out dependent and non-dependent steps means that you can improve test throughput. Hot simulators improve both performance and stability. WebDriver Agent enables an external test runner, and FB Simulator control allows this WebDriver Agent to be prepared in parallel on multiple simulators. And diagnostics will help you understand what your tests are doing. These are my three colleagues, Marek and Graham, who are here today. Feel free to say hi. So, yeah, thanks. Thank you very much.